motor, and in general, we will highlight how to control the speed from the steady state voltage equation, and we will start with the separately excited DC machine. Now, in the separately excited DC machine, we know that if I'm writing the voltage equation, who refresh my memory about the voltage equation? VT is equal
EA.
okay, EA
Always
RA IA plus LA DIA by dt. So simply I need to find a mechanism in order to do control. In the first stage, I will record the steady state operation, which means that any d by dt will go to where? To 0. So simply, this means that this part is going to 0, and I will end up with what? I will end up with EA, if I reorganize it, equal VT minus RA. And we know that EA is proportional with the speed, so it can be written as K phi omega. Correct?
Yeah.
And we know that the torque, the developed torque TD, is also can be written as K phi IA. Correct?
Yeah.
So there's a relation between TD and IA. Yeah. So I can write IA equal to TD over K phi. Correct? So now, if I plug this one here, I will get omega equal to VT over K phi minus RA IA over K phi. Yep. But simply we know that sometimes we need to find the torque speed characteristic. So I need to write the torque or the speed in terms of what? Of the torque. So I have the relation between the current, yeah? So I have the relation here between the current and the torque, yeah? So simply IA will equal TD over K phi, so this will equal omega equal VT over K phi minus RA TD over K phi square. Now, this one is actually the omega naught, and this one is actually delta omega, correct? Yes? Yeah? If there's no load, the current equals 0, the developed torque equals 0, and I will end up what? With the first term here, which is what? The no load speed, what we call it, huh? The no load speed. After that, there's a slope, which is what? Let's say has a relation or proportion to what? To the load or to the current. To the current. So, from here, I can judge how to control the speed. Yeah? So, for example, the speed has a relation with the VT. Also, the speed has a relation with what? With RA. Also, the speed has a relation with what? With the flux. Someone will say the speed has a relation with the load. I will say no. Yeah, it has, but this one I can't control it. I will never throw people while I'm driving the car. Correct? Yeah? The load, I should respect the load. And at the end of the day, I need to develop a load in order to, let's say, to achieve the demand loading, huh? The demand torque, let's say. So this is actually what's written here. So this is here, let's say, a graphical representation. The first thing you can see is what?
No load speed.
Is the no load speed or omega naught. After that, I'm having what? The torque speed characteristic of the machine. Huh?
Yeah.
Then let's assume that I'm having what? I'm having a constant load. The intersection between the load and the torque speed characteristic will specify what? The operating point. So now, where's delta omega? This is delta omega. Correct?
Yeah.
This is delta omega. Good. So now, from here, we can control the speed of the machine by adjusting or adding, let's say, external resistance to the armature. Yeah? Of course, here we can discuss two things. The first thing, if I'm designing the machine If I'm designing the machine, then I can design the armature resistance in the end of the day. But now, the other option is what? No, I'm having a motor and I need to control the motor. So the only possible scenario that I can adjust or modify the resistance is to increase the armature resistance. I cannot decrease it. Yep. Why? Because I will, in the end of the day, I will add what? External resistance in series with the armature. So now, this is the first possible scenario. Nowadays, no one uses it. Why? It's I square R. Yeah? Before, yes, before the revolution of power electronics, all of the control was what? Was actually the changing, or let's say adjusting the series resistance connected to the armature. The second one is what we call it the armature voltage. Now the first one and the second one, let's see. The first one will never change the no-load speed. Yeah? Why? The no-load speed has a relation with what? With the voltage and the flux. The first one only change the slope of the relation. The second one, which is the terminal voltage, will what?
Increase or change the.
It will change, it will shift. It will shift actually the torque speed characteristic down. Why? Because it will never allow to impose a voltage higher than the rated.
Okay.
Yeah? So my reference now is the rated point. So any voltage I will impose should be less than the rated if I need to adjust the voltage. So what I will do, I will shift the curve down with the same slope. With the same slope. Correct? The third one is what? Is the flux. If you notice here to the flux, the relation is what? Inversely proportional. Yeah? So simply here, I only have one possible scenario to reduce the flux. I cannot increase the flux. Because if I need to increase the flux, I need to impose a voltage higher than the rated in the field. And this is forbidden, correct?
Yes.
Yeah? Why? No. The first one is the insulation. The insulation can handle certain voltage. The second thing, if I increase the flux, the core will enter to saturation. Do you know the saturation? Yeah? The pH curve. You are, let's say, you are consuming more current than you need. Simply, huh? Why? Because saturated.
Okay.
Yeah? If I'm consuming a current more than I need, the remaining current will go to where? As a losses. Yes? So the only possible scenario is what? To reduce the flux. And this is what we call the flux weakening. From where weakening? I'm reducing the field. Yeah? I'm weakening the field. So this means that I will control the speed above the base speed, let's say, or the rated speed. Yeah? Sometimes I need to do that, yeah. Sometimes I need to do that. The last one is the field. And simply here I will reduce only the field voltage, which will reduce the flux, and the motor speed will be increased. So now let's see the first one. Or in general, if I need to control the speed, what, let's say, characteristic I need in order to control the speed, or good speed controller? The first thing, what are
Voltage control.
which means that I will never impose a voltage higher than the rated. I should respect that. What else? I should not exceed the maximum limit of the current. The unrush current should be limited, yeah?
Yes.
What else?
Flux and frequency.
By frequency, there's no frequency. It's this, yeah?
Field voltage.
What do you mean by that? I need a smooth transition. Yeah, imagine I need to go from speed A to speed B. I need to go in a smooth fashion, for example, yeah? Yes? What else? Hmm. What else?
Speed سرعة لحد معين.
Which means that I don't need to over accelerate or reach maximum speed over the maximum capability of the machine, let's say. Yeah? And this is a design parameter from the mechanical engineer. In general, the shaft can handle certain speed.
Choose the control to make the best efficiency.
Yeah, it can be, which means that the best harmony between the converter and the machine. Yeah, which is the smooth transition, respecting the voltage limit, respecting the current limit, and also I should respect the let's say the electromechanical oscillation. Yeah. Otherwise, sometimes you know there's what we call resonance. Sometimes if I reach a natural frequency, it can break the shaft. So the controller must also avoid this scenario. So soft transition can be sufficient speed damping. Over voltage must not be exceed. The magnitude of the inrush current should be kept under control, and finally natural electromechanical oscillation should be avoided. And this is, let's say, attributes of the good speed controller. Now, the first one here we'll discuss is the concept by adding a resistance in series with the armature. As we said, this one would never change the no load speed. It will change what? The slope only. Yeah? So if this one, let's say the rated torque speed characteristic, and I'm having here, I'm assuming I'm having what? A constant load. So point number one is actually the operating point under what?
No.
Under R equal RA. Yeah? Now the second one is what? RA plus R1 or R adjustment. Added one, added two, whatever. So here I'm adding what? A resistance. So R total will be greater than this one.
Yes.
The note of the speed will never change. What will change? The slope. Now I'm assuming here what? Constant load. So the current are constant, correct? The current is constant?
اللود
current.
constant. هيك الكرنت قل.
No.
Yes.
This is the torque speed characteristic.
Yes.
The torque is proportional with the current. If I'm assuming the flux is constant, and here I'm what? I'm doing what here?
Speed control.
Huh? Speed control by what?
Armature.
So simply, you know that in any system, if I need to adjust a parameter, I will fix all the other parameters.
Yeah.
So here I'm assuming what? Vt is constant. The flux is constant. Otherwise, I cannot do anything.
Yes.
This curve will be something swinging up and down if I'm changing everything. Huh? So if I need to study the effect of any parameter, I need to what? To fix all the other parameters. So here I'm fixing what? Vt, and if I need to fix it, it will be at rated. I need to fix the flux, and if I need to fix it, it should be where? At the rated. And only here I'm adjusting what? The RA. I'm adding a series in the armature circuit. And I'm assuming here that I'm driving what?
Constant.
I'm assuming that. Huh? So simply here the current is the same. The speed is changing. Huh? The speed is changing. Why? Because I'm changing the slope. What about if I add more resistance? What will happen to the slope?
Slower. The speed will be slower.
What about if I add resistance such that I will put the machine at hold position? What the meaning of hold position? Yeah, block rotor. Huh? So simply I need to adjust this curve such that the torque speed characteristic intersect with this point, correct? Correct? Okay? So simply here, let's see. I can go from point 1 to point 4. Yeah?
دكتور بس مش هيك point for useless إني أشغل المشين عليها.
Yeah. It's not like useless. Sometimes I need to calculate a load to put the machine at hold position. Huh? Yeah? Okay. Now, there's a value of the resistance that can put the machine at the hold position. Yeah? Sometimes I need to avoid this one. Sometimes I need this one to stop the machine. Yes? Yeah? Sometimes my target is to stop the machine. Yes? Or sometimes my target to calculate this value, not to add it, not to block the machine. Correct? So I need to know how to calculate this one. Good? Now,
بس لما حكيت الكرنت كونستانت على كل وحده ولا كلهم زي بعض؟
okay. Now, this is the torque speed characteristic, yes or no?
Oh.
Good. And you know that if the flux is constant, the torque is proportional with what? With the current. Thank you. So simply here, instead of the torque, I can write IA. Yes or no? So this point, and this point, and this point has the same IA?
Yeah.
Oh.
Yes. So this is a constant
Oh, okay.
current. Why? Because the load is constant, and I'm assuming what? The flux is constant.
Yeah.
If the flux is not constant, of course, there's something else will change. This torque speed characteristic for what? Under the assumption that I'm adding what? External resistance to the armature while fixing all the other parameters to the rated or at their rated values. Good? Okay. Now let's see. Let's make some challenge here. Let's assume that I need to start the machine. Yeah? While the current is never allowed to exceed twice the rated. Understood the problem is what? The machine at standstill. I need to run the machine. But I need to engage some kind of mechanism to limit the current from start until reaching one such that the current in the machine is never allowed to exceed twice the rated, and let's assume that this line is the rated value. Yeah? This line is the rated value. So if this line is the rated value, or let's put it here, yeah? Let's put it here.
Yeah.
So let's assume that this is the torque speed characteristic, and this is the rated current, twice the rated. It should be somewhere here. Huh? Now I'm here at standstill. I need to turn on the machine in one condition. I need to reach, let's say this one here, the rated point, such that the current is never allowed to exceed what? Twice I rated. I'm assuming that this line is for I rated, and this I need to do it by adjusting what?
Armature resistance.
So simply this can be seen as what? I'm having some kind of mechanism that assume it's a relay base. Correct?
Yeah.
And simply this is switch number 1. It's supposed to be yes. And this switch number 2, this switch number 3, and this switch number 4. So at t equal to 0, and this here plus minus V total. So at t equal to t0, all the switches are what? Open.
Open.
So I'm having the maximum resistance that I can impose.
Yes.
Yeah? I need to calculate this one. Yeah? From where? From which point? Yeah. 4, which is here. Yeah? Twice the rated. So at start, the current will be what? Twice the rated. Yes? So simply at start, I should be here. Correct? Yeah? So at start, should I do this one? It should be here somewhere. No, not good.
طب جرب كنترول زد ده صعب.
No, Control Z is not working. Control Z is not working. I did that in the first step. Actually, I was searching for a shortcut. I could not find. So, let's be clever. By changing the thing to this one, and let's do space here. The same problem, huh? Yeah. It's supposed to be, huh?
Yeah.
So let's remove that one. Okay. So the first thing here, I should calculate this point, correct?
Yeah.
How to calculate at this point? The voltage equal to what? Thank you. The current equal to what?
Twice
So can I calculate R total? Yes. Yes. If I have R total, I will subtract it from RA and I will get the additive R or the added R. Correct?
Yeah.
Yeah. So after that, what will happen? You know that the machine will try to accelerate. Yeah? Following what? The second line, let's say, a torque speed characteristic. Until I'm reaching where?
1.3.
Now the current is what? Equal the rated. I should switch now. Yeah? By switching, this means what I will do?
Change the armature.
I will reduce what? So one of the switches will be closed, correct?
Increasing speed.
Yeah? So one of the switches will be closed. Let's assume that this switch is closed.
Okay.
Now, the second line is forbidden. I should go to where? To the second line, correct?
Yeah.
Of course, this plot is not accurate. Why? Because now here I should go to this point. So I should have a torque speed characteristic that is crossing this point, correct? It's hard to control it, but I think you're getting the point, correct?
Yeah.
Then, now I'm here, at this point. Yeah? Let's say point 1, 2, 3. Or start. How to calculate R here now?
The voltage rated.
The voltage is rated,
Current.
the current is twice, and speed from where? From the first scenario. Now here, omega equal to 0 at this point, correct?
Yeah.
Now while I'm accelerating at this point, what I'm having? I'm having R total, I know it. The current, I know it. Vt, I know it. I can calculate what? Omega. Omega. Not delta omega. This point. Of course you have delta omega. But simply, I need omega. Because if you have delta omega, you should subtract from omega to get what? Omega. Yeah? Now at this point, what I'm having now? I'm having the current, I'm having the voltage, I need EA. From where? From the previous point. Good? So now I can what? I can calculate the needed, let's say, resistance to be adjusted in order to go from 0 to the rated speed without increasing the current more than twice, for example. You are getting the point? Good. So this is another example. Can you help me with that? Yeah.
سؤال أقرأ
If you
1500 volt DC shunt motor drives a constant torque load at speed of 1200 RPM. The armature and the field resistance are 1 ohm and 1500 ohm
respectively.
The motor drives a line current of 10 amperes at the given load.
Okay. So simply thank you. So simply here what I'm having, a shunt connected. Yeah? And this shunt connected is connected to a constant load. Yes?
Yeah.
And the load is rotating by speed 1200 RPM, 1200 RPM, correct? And it draws a line current. This line current is not armature current. This is the total current,
Yes.
Yes.
which equal IA plus IF, because this one is what? Shunt.
Shunt.
Yes? Now, and the line current is equal to what? To 10 ampere. Now, here I need to add a resistor in the armature circuit such that the speed drop by 50%. So I know the speed, the target speed, yes I know it.
Yeah.
50% multiplied by 1200, 600.
600.
Yes? Yes?
Yeah.
Good. Here, the field is constant.
Yeah.
Yes, why? Because I'm adjusting the armature resistance by adding what?
External
Resistance. The armature circuit by adding what? A resistance. Huh? If I'm adjusting the voltage, in this case,
Then the field will
the field will change. Yeah? But here simply I'm fixing the field by fixing the total supply voltage, let's say, and only I'm adjusting the armature circuit by adding an external resistance. I need to calculate this resistance. Then I need to calculate other resistance that if I put it, I will get the hold condition. Yeah? Good? Okay. So the first thing, what I need to calculate, I need to find IA. IA equal to what? IA equal to what?
IA.
You know that is IA will equal I line minus IF.
Yes.
I line is given? It was 10. IF I can calculate? Yes, I can calculate with no time. 150 over 150, I think, correct?
Yes, 150.
Yeah? 150 over 150 ohm. Yeah? So this will be 150 over 150, and according to the Bachmann theory, it will be eaten, and I will get what?
No.
9 amps.
9. Yeah? 9 ampere. Good? Okay. Now, the flux is constant. Yeah? The flux is constant. If the flux is constant, then IA1 was equal 9 ampere. Yeah? And we know that if the flux is constant, then the current will be constant.
Yeah.
Because I'm driving what? A constant load. Yeah? So IA1 will equal to IA2. Yeah?
Yeah.
So this also will equal to what? IA2. Now, if we recall the voltage equation, VA is equal EA plus RA IA. Now this one is already given.
Yeah.
This one is given. This one
Need to be.
I need to find it. Yeah? And simply this one is changing because here I'm having two positions. I'm having speed 1 and speed 2.
Yeah.
Yes? Now let's see. We know that EA is equal K phi
omega.
omega. Yeah? So EA1 will equal K phi omega 1. Yes? So EA2 will equal to what?
K phi omega 2.
K phi omega 2. So simply I can do what? EA1 over EA2 should equal to what? Omega 1 over omega 2. And because I'm having n, I can write n1 over n2.
Yeah.
Yeah? Yes? Good. Now, if I need to calculate EA, this is equal to what? VA minus RA IA. Correct?
Yes.
So simply from here, I can say that EA1 should equal VA minus RA1 IA1. Yes? Over EA2. Yeah? And this will equal to what? VA minus RA2 IA2. Yes? And this will equal to what? N1 over
N2.
N2. Yes?
Yes.
Yeah? Good. So now I think we can solve it.
Yeah.
Yes? Why? Because this one is given, I think it's 1 ohm.
Yeah.
This one is the 1 plus R add. The current are the same.
Yes.
The speed already we know. N1 is 1200, N2 is 600.
Yeah.
And V is the same, so I have what? Single equation with one unknown. Correct? So I can solve? Yes, I can solve. So if we do the math, the same thing, huh? So if I do the math, simply R added will be equal to 7.83 ohm. Good? Good. Now, the second one was what? I need to what?
Hold.
I need to find the resistance that I should add to the armature circuit such that the machine would be at where? At the whole position. So, omega equal to what?
0.
So, the back EMF equal to what? EA equal to what?
Yeah.
0. Yeah? The back EMF,
Ah,
K phi omega. Huh? If omega equals 0, then the back EMF, the induced voltage will equal to 0. Yeah? If I need to generate a voltage, I need the flux and rotation. Yes? So, in this case, what I'm having, V is equal Ri. So, R total is equal V over I. And the current is what?
Constant.
The current is equal to 9. Yeah? So, simply, yes. Yep. Minus the 1 ohm.
Minus 1.
Because I need to calculate what? The added resistance. Yes, so it's very straightforward. Simply, I need to calculate at point number 4.
Yes.
Speed equal to 0. So the back EMF is equal to 0. So I will end up with VA minus IAR total equal to 0. So if I rearrange this one, I will get the R added equal 15.67 ohm. Good. Straightforward. Yep. Good. Nowadays, no one uses this method. Why? Because here I will, let's say, add losses. The system I square up. But before, let's say, the power difference, this is the only mechanism that we can change the speed. Now, what about if I need to adjust the armature voltage? As we said, if I'm adjusting the armature voltage, I'm shifting the curve with the same slope down because I'm reducing the voltage from the rated until, let's say, the minimum voltage or the zero. So let's assume that this is the case. The same thing here, I'm assuming that I'm driving a constant load. And let's assume that this is the point of the operation or the operation. Yep. And here I will change the voltages in 3 steps. V1, I will go to V2, then V3, then V4. In this scenario, such that V1 is greater than V2, is greater than V3, is greater than V4. So this one is what for V1. V2 will be above or down?
Down.
Under it, the same slope.
Yes.
Yeah? V3 carry. Under V2, the same slope. V4 carry. Here, let's assume that this one will put the system at hold position.
Okay.
Here are the same. I can ask you the same. I need to calculate. Let's assume this was separately excited. Because now I need to adjust what? The voltage. Yeah? By the way, you know that adjusting the resistance is actually adjusting the armature voltage. According to what? Oh, no. Or KVL. I'm doing drop voltage. So the effective voltage that imposed to the armature is the certain voltage I need. Yeah? But in that case, what I did voltage divider. Yeah? Yes? Here, let's assume that no, I have another mechanism. I have power reference, I have chopper, I have converter. So simply I can adjust the voltage directly. Yeah? So if I will do so, let's assume that I'm having separately excited. Otherwise, I will affect the field, and there's the relation between the field and the armature circuit, and the relation will be non-linear. Huh? Let's assume that I'm doing here armature controlled, separately excited. So I will adjust the voltage such that the machine at hold position. How to calculate this one? Very simple. Yeah? R multiplied by what? By the current. Yeah? By the current, which is proportional, let's say, to the T total. Huh? If this one's the rated, in this case it will be the rated. If this one twice the rated, that one will be twice the rated. Yes? Here are the same. Huh? I can say that I need to adjust the voltage and level such that the current is never allowed to exceed 3 times the rated. Huh? 2 times the rated. This who specified? Twice the rated, 3 times the rated, 4 times the rated, 6 times the rated. Yeah. Let's say the transient capability of the machine. Yeah, because here I will never operate for long time. Yeah. This one, yes, I will operate for long time. Here, no, this is a transit, let's say. Here are the same. So let's assume that I'm forgetting line number 4. Okay. Yeah. So this will be what? The first point I should specify. So here I need to calculate if I'm having the same slope. Of course, it will be not. So what about to make it here? It will be more interesting. Yeah? Let's forget this one. Sorry for that. Because you know that the line number 4 is the, let's say, the minimum voltage I can have to intersect with this one. But simply here I will go to regenerative braking. Yeah? I was thinking to plot another one, but simply it will never be the same slope. So now I'm shifting to this one here. Huh? Now here I'm having this one. Let's say this one T rated, and this is twice the rated. Assumption. So this will be T rated, and this will be 2
2
times the T rated. So I need to calculate before how much voltage I need to impose at starting. Now let's see, omega equal to what at 4? 0, thank you. Yeah? The current equal to what at 4? Yeah, 2 the I rate. Yep. And the resistance, I know it. Yeah?
Yes, no.
So simply what I'm having, V is equal Ri because EA is equal to 0. And this actually the calculation of the starting current. Yeah? In the machine lab, for example, one of the parts that you need to add a resistance in series in order to limit, let's say, the starting current. Here I will limit the starting current by what? By adjusting the voltage. So this is also another method that I can use to adjust that. Then after that, the machine will start to accelerate, so I will go here at 0.4. Now, I will accelerate until reaching this point. After that, I will change another voltage. Yeah?
Yes.
So here, what I will calculate from this point? The speed. Then I will go here. I will calculate what? The new voltage.
The new one.
Why? Because here the speed is given, Yeah?
Yeah.
the current is given, so the only missing thing is what? Is the voltage I need. It will be somewhere here. And I can go until reaching what? The rate value. In steps, yeah? In steps. And here, because the slope are fixed, the step will be fixed. So if you calculate the first step, it was 10 volt, the second one will be what?
10
Another
volt.
10 volt. Why? It's a linear, the same slope.
Okay.
Yeah? And here is what I'm
Constant
restricting the current to be from the rated to twice the rated. Now for the field, if I need to adjust the field, we know that if I'm reducing the field, the speed will what?
Increase.
Will increase. So let's assume that this is my base curve. Now here, the same thing. The armature voltage or the VT is what?
Fixed.
Fixed. I will never change anything in the armature cell. Only I'm modifying what? The field. Either by adding a resistance or adjusting the voltage if I'm discussing separately excited. Yeah? So this will be the point number 1, which is the operating point at the rated conditions. Yeah? Now I will do 2 steps. I will go from the first field voltage to the second one and the third one, such that I'm reducing the field voltage. So now this line, or I need to plot another line. Should it be above this one or under?
Below. Yeah, above.
Above.
Speed.
Above.
Speed.
This is the first thing. So adjusting the field will adjust the no-load speed. Yes? And it will adjust the slope. Yes?
Yeah.
Yeah? So now the slope is not the same. Yeah? The slope of the curve is not the same. So simply, you see the slope? It's not the same. Why? Because I'm reducing the flux. If I reduce the flux more, I will go to point number 3, and the slope will be what? Increasing. Not in the same fashion as the armature voltage control, where the slope was what? Constant. Good? Now, here, can I reduce the field to any value? No. So, what will restrict me?
Rated,
The speed.
IF.
The speed. The maximum speed, correct?
Yes.
The maximum speed. Yes? So simply here I can reduce the voltage until I'm reaching what? Certain maximum speed that can be a design parameter. Here, the current is constant in point 1, 2, and 3.
No.
No. Why?
No, phi is.
Yeah, because phi is changing, but the torque is constant. So the torque in point number 1 is the developed torque in point number 1 is equal to the developed torque in point number 2 and is equal to the developed torque in point number 3. But the current is not the same. Why? Because the torque is equal what? K phi I. So if I reduce the flux, I should increase the current such that the torque is what?
Constant.
Constant. Correct? Good. So this is another example. Who can help me with that? Can you help me?
150 volts DC shunt motor drives a constant torque load at a speed of 1200 RPM. The armature and field resistance are 2 ohm and 150 ohm respectively. The motor draws a line current of 10 amperes. Assume that the resistance is added in the field circuit to reduce the field current by 20%. Calculate the armature current, motor speed, the value of added resistance, and the extra field losses.
Okay, good. So simply here I will do what? I will do flux weakening. I will control the flux without changing the voltage imposed to the armature. So the only thing that I can do for the shunt is to add a resistance where in series with the field. Yeah? A resistance in series with the field. Yeah? Yeah, to reduce the field. So simply, this is the thing that here I will add what? A resistance. Correct? Now let's see. At case, the first one without adjusting any at the rated field, the current, the armature current is equal to what? Then, okay, it's given actually, I think it was the line current was 10, correct? Yeah? It was 10.
Yes.
Yeah, and this one was I think 150, and here it was 150. So this one is IA1, let's say, will equal to 10 minus 1, which is 9 ampere. Yes?
Yes.
Good. Now, what we did here is to add R external here, or R added in the field, such that the flux is reducing by 20%. Yes? So, in terms per unit, if the rated is 1 per unit, then the new flux is what? 0.8 per unit, correct? Yes? Good. Now let's see. In the first stage, we know that because I'm driving a constant load, then TD1 should equal to what? 2D2. Yeah? Now, the TD1 is actually equal to K phi 1 IA1. This must equal to what? K phi 2 IA2. So simply here, this means that phi 1 IA1 is equal to phi 2 IA2. And I need to calculate IA2, correct?
Yes.
So IA2 equal to what? Who can help me with that?
Phi 1 over
Phi 1 over phi 2
IA1.
IA1. So simply, phi 1 over phi 2 is 1 over 0.8, correct?
Yes.
Multiply by IA1, we'll calculate here 9. And if we do the math, this will equal 11.25. 11.25 ampere. So do you see, in order to maintain the same load, I need to increase what? The current. Yes? Why? Because I'm reducing what? The flux. So this is the first part. The second part was what? What I need to do? Okay, so this one, the armature current, the motor speed. Now I need to calculate the motor speed. So at the first one, I was operating here somewhere here at omega 1. After the field is reduced by 20%, I will operate, let's say here, at omega 2, and of course omega 2 is higher than that.
Yes.
Okay. Now let's see the same thing. Do you remember EA
Yeah.
equal to what?
K
K
phi.
phi.
So EA1 equal to K phi 1 omega 1. Yeah? And EA2 will equal to what?
K
K
phi
phi 2 omega 2. So, yep. So this will equal to what? The first one, EA1. VT, yeah, minus R A I A1. And this will equal to what? VT, I never change VT. minus RA, I never change RA. But I have IA2, correct?
Yes.
Yes? So simply if I do the math here, EA1 over EA2 will equal to omega 1 over omega 2, which will equal N1 over N2.
Yes.
And this will equal 150 minus.
دكتور
Five.
فاي مش constant.
Sorry. So this will be phi 1 omega 1 over phi 2 omega. Yep.
Yeah.
Good? Good. So what was given?
معطينا ان
Yeah, n is given.
Yes.
N is given. What else?
N is given.
BT RA
VT
Yeah, we have IA here, and this is IA2, and this is IA1. We have it. The flux, 90. We have a relation, huh? Correct?
واحد وربع عنوان على ان
Yeah. So similarly, we have, I think, the flux 2 is equal 0.8. The flux one, correct?
Yes.
Why? Because it was a reduction by
20%.
20%. Correct? It was a reduction by 20%. Good. Okay. So simply now, this will equal to phi 1 over phi 2 is 0.8. Yeah? And instead of omega 1, I can write n1 because I have n over into, and this will equal the VT is 150 minus R was 2 or 1? 2 multiplied by 9 over 150 minus 2 multiplied by 1.25. Yep. If I do the math, I can calculate the N2. So this is what is already written here. So N2 is equal 1148.86 revolution per minute. Good. What else is written? I think I need to find the value of the resistance. Yeah?
The value of the resistance
And the
losses.
How to calculate the value of the resistance that I need to add to the field circuit?
بحسب الفولتج اللي عند هاي السبيد.
You know that the flux the flux phi f is a proportion with IF factor. Good. Yeah. So simply from here, phi 2 over phi 1 is equal IF2 over IF1. Correct?
Yeah.
So simply this will be what? I need to calculate what? IF2, and IF2 will equal to what? 0.8 multiplied by IF1, and IF1 is what if we do the math? 1. So IF2 equal to what? 0.8. Yeah? So if I need to calculate the field current here, IF is nothing more than what? VF over RF total, huh?
دكتور بقدر اعمل ابريت المصدر على السرعه اعلى لفتره طويله؟
Yes. Actually, this is the idea behind flux weakening, and the speed that I can reach, is limited by the maximum speed, and the maximum speed is what we say it's a design parameter from mechanical engineering, how much speed that the shaft can handle. Yeah? Later on, I will plot what we call the constant torque region and the constant power region. In the constant torque region, I will assume that the torque is constant, which means that I can provide the maximum capability in terms of the torque at certain speed. After that, I should enter to what we call the flux weakening. The flux weakening is from the base speed until where the maximum speed, and all of that curve is valid for the continuous mode of operation. Good. Now, here, if I need to calculate RF total, so RF total will equal to 150 over 0.8, and this equal to what?
187.5.
87.5. So, yeah. Okay. So RF add equal to 187.5 minus 140.5. So now the power losses on the field equal to what? IF squared over multiplied by R, sorry. So this will equal to 0.8 squared multiplied by 37.5, and this will equal, if you do the math, if equal to 24. Yeah, 24. So this will equal 24 watt. Good. So
مش المفروض RF كامل ناخذ؟
I think it was asking about how much losses it will increase. Yeah. If I still remember that, let's change to the. Yep. And the extra. The extra. So here it should be, let's say, you should read the question carefully and be careful, because sometimes maybe I will give you the two options or two answers, the first one and the second one, but simply I'm asking about what? The extra. The same thing. Sometime I will give you that how much resistance I should add to the field circuit or the armature circuit. I will give you all the R total and the actual R. But I'm asking for what? Add, not the total R. Yeah? So you should be careful. Huh? Should be careful about that. So this is a summary regarding the strategy of the speed control, and let's assume that I will recall the separately excited machine. So simply here, if I need to control the speed from 0 to the rated speed or the base speed, I will do a armature voltage control. Here I'm neglecting adding any external resistance to the armature, yeah? Because either it will add losses, or simply in the end of the day, it actually adjusting the armature voltage, yeah? Voltage divider. Now, if I need to go above the base speed, in this case, I need to go to flux weakening, yeah? Which means that I need to reduce the flux, yeah? I need to reduce the flux. Now, we know that the torque is proportional with the flux and the current. So if I need maximum capability of the machine, the maximum torque, if I need to enter to the field weakening, I must fix the current to the maximum value, correct? So for example, if I'm telling you that the current is never allowed to exceed twice the rated, then the maximum current will be what?
Twice the
If I'm telling you that the current is never allowed to exceed 3 times the rated, then the maximum current is what?
3 times.
So if I need to achieve the maximum torque, I will put the current to be where? The maximum. Yes? Why? Because here I will reduce the flux and the flux weakening. Yeah? So I need to maintain the current at where? At the maximum value. Now what about the developed power? We know that in the electrical machine, in the DC machine, the developed power is nothing more than the back EMF multiplied by what? By the armature. Correct? Now, if I'm reducing, let's say, the flux, the speed will what? Will increase. Yeah? So EA should be constant. EA should be constant. Why? In the flux weakening, I'm adjusting VT, and the current, I'm assuming, in order to achieve maximum torque, the current is constant at where? So EA should be constant. Yes? EA should be constant, yes or no? I'm fixing VT, yes? And I'm fixing the maximum current.
لا اي مش
لا مش
طيب
مش
Just- Now, I think you agree with me that VA is equal RA IA plus EA. So this one can be reorganized as VA minus RAIA. Yes? Now, if I need to enter to the flux weakening, VA is the rated, yes or no?
Yes.
So fixed, yes?
Yes.
Now, for the maximum capability or the maximum torque, I need the current to be maximum. Yeah? So it's fixed. Yes? So if the current is fixed, and the voltage is fixed, and the resistance, I never change it. Yes? So EA should be what? Fixed. Now, how come EA fixed? While I'm reducing the flux, I'm increasing what?
The speed.
The speed. Correct? Yeah? So EA is what should be what?
Constant.
So in the flux weakening, EA should be what? Constant. That's why in machine you call it the constant power region, EIA. Huh? Yes? And in the voltage, armature voltage control, you call it what? Constant torque region. Huh? Constant torque region. Good? Good. So simply if I need to control the speed from 0 until, let's say, twice the rated value, what I should do? If I need to control the speed in wide speed region, which means that I need to cover very low speed and, let's say, higher than the rated speed. So I should do what?
Both.
Both. Yeah. But simply I cannot do both at the same time. I need to have a point to switch between what? The armature voltage control to where? To the field control. Yeah? This depends on the maximum current. If the maximum current is the rated, then the switching will be what? At the base.
speed.
If I'm allowing the current to be twice the rated, it will be less than the base speed. Now, this one actually must be fixed, correct? EA is equal to VA minus RAI. Now, at the switching point, you know that the speed before this point and after this point at the same instant are the same. Good. Yes? Yeah? Good. Now, if the current is higher than the rated, then EA will be less than the rated or no?
Yes.
Yes. The flux now before switching is constant, yes? So this speed, less than the base speed, the rated speed or higher? Less. So now I'm in the point of the switching, the speed before the instant of the switching and after the instant of the switching are the same. Yes?
Yes.
Yeah? So now I'm doing the switching before the base speed. I will give you example regarding that. Yeah? Good? Okay. So now let's try to discuss the armature and the field control in order to achieve, let's say, wide speed region of control. And in the first stage, I will plot the curves under the assumption that I'm having 1 per unit in the armature, which means that the rated what? The rated what?
1 per unit.
1 per unit, the rated current. The rated current, correct? Good. Now, in the first stage, the torque developed TD is equal to what? K
Okay.
phi
I.
I. Yes?
Yeah.
Now, in the first stage here, I will plot what? VA control. Yeah? V armature voltage control. If VA control, then the flux is what?
Fixed.
Equal VAN. Yeah? The rated value. Yes? Good. Now, TD rated will equal to what? K phi rated
I.
multiplied by IA rated. Now, if I'm writing a normalized function, Fn, you know the normalized function, the per unit. So any function in per unit equal to what? The actual value over what?
The base
The
value.
base value. And let's assume the base value is what?
Rated.
Is the rated. Yeah? So here, this will equal to what? This will equal F over F rated, correct?
Yeah.
So let's write here TD normalized. And this is equal to what? It will equal to what? Phi normalized, IA normalized, correct?
Yeah.
Now, if I'm assuming that IA is equal 1 per unit, then the curve of the developed torque will equal the curve of the flux, yes or no?
Yes.
under the assumption of this one, correct?
Mhm.
Now let's see, the power developed equal to what? EA, IA. The same thing, the power developed normalized will equal to what? EA normalized multiplied by IA normalized. And if I'm assuming IA normalized to equal to what? Or IA equal 1 per, I rated, so IA normalized equal 1 per. Yeah? So here I'm assuming that IA is equal IA rated. So simply IA normalized will equal 1 per unit. So if IA normalized equal to 1 per unit, this means that the care of the power developed is equal to what? So simply here I need to plot only two curves. Yeah? The normalized torque, which indicates or identical to what? To the flux, and the back EMF normalized, which identical to what? In per unit. Yes, in per unit. Good. So now let's try to plot that. So this is the speed, and I'm plotting what? I'm plotting TD, phi, EA, and BD with respect to omega. With respect to omega. And here, this is the base speed. Let's assume that this one is omega base. Now omega base here is equal to what? Now let's see. VA is equal RA IA plus K phi omega. And this is what we call EA. And now EA is equal VA minus RA IA. Because this one is the rated at the base speed. And this one is not changed, it's the actual value. And IA here is assumed to be what?
1 per unit.
So this means that EA is equal 1 per unit also. Yeah?
Yes.
Which indicates that omega base is also equal to what? 1 per unit, which is the rated value. So here the switching will be where? At the rated value. Okay. Now, from here to here, from omega less than or greater than 0, less than omega base, I'm controlling what? The armature voltage or the field? So, the field is kept constant as the rated value, correct? Yes? So, the torque will equal to what?
Final.
1 per unit.
Yes.
Yes?
Yes.
Yes? 1 per unit. So, simply here, so this curve is actually for what? For TD normalized and phi f normalized, correct?
Yes.
Now, while I'm increasing the speed, EA will increase or no? The back EMF, while I'm increasing the speed, it will increase. Until reaching where? Until reaching what? The 1 per unit. Why 1 per unit? This one. Good. At the switching point. So this one is also will be increased.
linear.
Yeah. The flux is constant. Yep. Smooth. The problem in the height. I think this one's okay. Yeah.
Yes.
Let's clean that. Huh? Okay, good. Okay. So this curve for what? EA normalized and the power developed normalized. Now after that, what will happen?
Adjusted.
The EA
when omega greater than omega base, I'm fixing now the armature voltage and I'm adjusting what? The field. So the field will start to reduce, correct?
Yes.
And the same, this one should be blue. Blue.
Speed frequency.
This should be blue. Okay, I have the black, so let's put the black one. So while the black, where is it? Black. So after
Highlight and
بس highlight and شمال.
okay, let's remove this one. I think this is, by the way, if you can, let's say, give a recommendation for the Microsoft to add a shortcut or a toolbar. Yeah, it would be very nice.
So القلم في كبسة عليه.
Yeah, but I think that one is for up and left and right.
في applications
Yeah.
بنزل له تعمل شورت كت مثلا undo or erase.
Yeah, I think so, but this you need to customize.
Yes.
Yeah.
تمام.
So treat me as بسيط. You know بسيط? So simply, this one should be constant. And this is a nice line. Until I'm reaching what? Omega max. Yeah? And let's change the color to blue it was, huh?
Yes.
And now increasing the flux will reduce, reducing the flux
Increase
will
the
also increase the speed and reduce the torque. Okay? So also this is the what we call the constant power region, and this is what we call the constant torque region. So here we have VA control, and here we have the flux control. Good. Okay.
دكتور بالفلكس كنترول التور كونستنت صح؟
No.
مش احنا كنا نحكي
Just a minute. So, sorry to interrupt you. Now, this is what we call it the motor capability, which means that the motor can drive any point here, the maximum capability. Yeah? But is the motor will operate at this point? This will decide what? The load will decide that. Yeah? Understood? So here what I'm writing the motor capability. When I say here the torque is constant, this does not mean that the mechanical torque is constant. I mean at this point the machine can provide constant torque from 0 to omega. Yes? Can provide this torque. Now this torque equal to what? 10, 20, 50, this depends on what? Yes? Yeah? So here I'm assuming that the maximum capability of the machine is what? The rated. This is continuous mode of operation. I have another curve, which is a wider curve, and this one we call the transient capability. Yes? Now here the same. This is the field weakening. Huh? I can go on speed omega max. This omega max can be twice the rated, 3 times the rated, 4 times the rated. This can be linked either from the mechanical constraint. I can give you that the shaft can handle only the speed, or I can tell you that the minimum voltage for safe drive, the minimum voltage in the field cell, huh? For safe drive is 20% of the rated voltage. So now you have what? You have a clue, let's say, to calculate what? Omega max.
Yes.
Yes? So this one in general, either it's given directly or it can be linked with what? With the minimum field voltage. Understood? You have any question? No? The others? فيش others.
دكتور بس لو كان مثلا عندي اللود كونستنت وانا الفيلد كنترول ريجن تمام بس اضاعف الفلكس حيزيد اي اي صح؟ فحيتغير عندي اي اي صح؟ ولا لا حضر كونستنت؟
You are missing the one point. Here I'm plotting the curve, assuming that I'm fixing the maximum current. So I'm fixing the maximum capability of the machine, which means that the machine cannot drive a load more than the rated load in the constant torque region. And if I need to go above that, I need to reduce the load. Yes? Just a minute. I need to finish with him. Yeah? Do you remember when I told you that for the maximum torque, I need to specify maximum current? So now if I'm telling you that the machine can handle twice the rated, so this curve will be here. Yes? Yeah? So now the curves for the flux and the torque are not the same. Correct. This was valid because I'm assuming that what? IA is equal to IA rated, which 1 per unit. In the end of the day now, the curve for the torque is the same as the curve for the flux. Yes? If the current was twice the rated, then now TD is equal to what? 2. And by the way, this is for you. In VA control, all the time, the flux normalized is equal to 1 per unit. In the armature voltage control, all the time, the flux normalized is 1 per unit. Correct? So now, if I'm telling you that the current can be twice the rated, then I should put another line here with 2 per unit to what? Yeah, for the torque. Yes? Yes? Good. But simply here I should switch before the rated. Before the rated. Yes? Good? Good. So let's take example, numerical example. Maybe the numerical example will be very... I have a numerical example, I think. Yeah? Yes, I have a numerical example. This one. Oh, good. So, simply here what I'm having, a separately excited DC machine, which has the following rating and parameters. I'm giving you all the information you need. Now, I need to plot all the characteristics, which is the flux, the torque, the back EMF, and the power developed. Yeah? If the armature and the field current are not allowed to exceed their rated values. Yes? So simply here, this one I can put with no time. I will switch out at 1 per unit. Then I will draw 1 per unit line. Yeah? Then the flux should be reduced. Yeah? From where? Here. Where is it? Yeah, this one. The field current are not allowed to exceed their rated value. And the minimum field, it must be written here, somewhere here. The minimum field is, I think, 10% of the voltage. Maybe I missed to write that, but yeah, I should add that one in order to complete the curve. So this supply is variable from 0 to 1 to 0, both for the field and the armature. And the minimum, VF minimum, is equal 12 volts. So this will specify what? Omega max. Yeah? So simply if I need to solve this one with no time, I will plot something like this one. I will say here omega base equal 1 per unit. Then I will draw a line here, reduce it here, and this will be 0.1. Yeah. Yes? And after that, and this will be what? Omega max. And this will be 10 times omega base. Yes? And after that, if I need to plot, let's change the ink. Color here. To red. So this will go to 1 per unit. And after that, this will be fixed. Yeah? 1 period. Actually. Now, if I need to find the values for that, we can do that. In the first stage here, I need to calculate what? IA rated. IA rated is given? No. Can we calculate it? Yes. How to calculate IA rated? Now, P out equal to what? P multiplied by omega. Omega is given. I can have it. Huh? Yes, I can calculate omega. And P out, I have it. So I can calculate T rated. Yes, I can calculate T rated. And if I calculate T rated, can I calculate IA rated? Where is it? This one. Do you remember when I told you that if KB is given in volt second per rad, this actually is KT, which is K5? Yeah. So now here, I can calculate the rated current as T rated over the KT 0.764. Yeah. So simply I can, if I need to find values, not in per unit. In per unit, I don't need to do that. Why? Because this one, the torque is 1 per unit, correct?
Correct.
Yeah. Why? From where?
Not allowed
To exceed what?
the rate.
The rated values. So simply, this means that IA is equal 1 per unit. The flux, of course, here will be 1 per unit. So the flux rated is 1 or normalized, let's say, in the VA control, 1 per unit. Now, the minimum flux equal to what?
0.10.
Yeah, from where here? Yeah. We know that the flux is proportional with what? With IF. And IF is proportional with what? With the voltage. Yes?
Yes.
So 120 0 volt is giving me the rated field. So 12 volt will give me what? 0.1 of the rated. Yeah. Yes? So simply this means that this value will equal to what? 0.1. Yeah. Now the same thing. If I need to calculate omega max, I told you that it's 10 the omega max, correct? Now the flux can be greater than 0.1 or less than or equal 1 per unit. Yes?
Yes.
At 1 per unit, at where? At VF equal to what? 120 volt. And 0.1 where? When?
12.
And VF minimum is equal to 12. So we know that the flux is inversely proportional with omega, correct?
Correct.
So at 1, it will give me 1 per unit. Yes? At 0.1,
10
1 over 0.1. So it will be 10 what?
per unit.
No, I will give you something more direct. It will be 10 the base speed. Yes. So if the base speed is 1, it will be 10. If the base speed is 0.7, it will be what? 7. Yes?
Yes.
Yeah? Good? Good. Now, let's repeat the same one, except that the current is what?
Allowed to be
300. So 3 per units. The current is what? 3 per unit. I need to calculate what? Omega base. The omega at which I will switch, correct? Okay. So in the first stage here, let's calculate the rated, EA rated. Can you give me this one equal to what? No, yeah, it's 1 per unit, but simply here I need to calculate it in order to find the normalized value. Huh? So this will equal to what? The voltage was equal to what? I give you the voltage, 120. So 120 minus RA 0.8. Now I need to calculate what? IA rated. IA rated, who has a calculator? Or should I take it from my notes here? Yeah. Now T rated will equal to the power, which is the 2.625 multiplied by 745.6 over 1313 multiplied by over 30. And this one, if we do the math, it will equal to 14.23 Newton meter. Now from here I can calculate IA rated, which will equal to 14.23 over the 0.764, and this will equal to 18.63 ampere. So now this will be what? 18.63. If we do the math, this will equal 105. No, I need that.
ما مضروب ما مضروب بالماكس 380.
No, just a minute. I'm calculating here what?
The rated.
The rate.
Okay.
I need to find the base value. Here, I don't need the base value, the rated. So it will be 1 per unit. Now here, no, I need to calculate the values. Yeah? So that's why I need to calculate the actual value. Then I will do the normalization, the per unit. Yeah? So this will equal to what? The 105.1, huh? 105.1. Now, let's calculate EA at 2. This one. Now, the current is what now here? 3 times. The voltage is fixed. So this will equal to what? 120 minus 0.8 the RA, multiply by 3, multiply by 18.63. If we do the math, this will equal something, this will equal 75.29. Yep. 75.29. Good. So now, EA normalized equal to what? You know the normalization in per unit. The actual value over the rated. Yes? So this will equal to what? 75.29 over 105.1, and if we do the math, this will equal 0.716. Yes? Who can give me omega base equal to what? Remember, the speed before switching and the speed after switching are the same, which means that I'm speaking about this point. Huh? Here, roughly speaking, I'm speaking about this point, correct? It's supposed to be this point. Huh? So at this point, the speed at this point, by the way, I'm at two curves. The end of the constant torque and the start of the constant power, which is the same point.
Yes.
Yeah? Good? Good. So who can give me at this point omega base equal to?
7.16.
Yes, it should be 0.716. Why? Because EA is equal to what? K phi omega. And at that point, phi is equal to 1 per unit. Yes? So in terms of the per unit, omega will equal to what? To EA. Yes? Good. So here, if I need to plot this one, so I think the second one here is free for me. So let's try to plot this one. So now we say that omega base is equal to what? 0.716. Yeah? Per unit, huh? I'm putting in terms of the per unit. Now, this one, this line here is phi f normalized is equal to 1 per unit. Why? Because in VA control, the flux is constant. Now, I need to plot the torque normalized. 3. It will be 3, huh? It will be 3. So it will be somewhere here, huh? Let's assume that this one is 3, huh? I know it's not. Now it's 3. Which means that I'm cutting the X, huh? Good? Good. What about the back EMF? It will start from 0 until where?
0.716.
Yes, it will be 0.716. The back EMF. The back EMF is equal to what? EA is equal to K phi omega. And in the voltage control, armature voltage control,
The phi
phi is constant. So it will be the same, huh? So this will be the 0.716. This is the 3 per unit. Huh? This is the torque. This is what the EA. All are normalized. The power developed equal to what? IAEA. So it will be 3 the EA. So it will start from 0 and end where? At 2 point something, 2.1.
Yes.
Yeah?
3 times.
Can you calculate it? It should be 2.1 something.
48
No,
Ah,
2.148.
So it will be somewhere here. So this one is equal to what? 2.1448. And this is for what? The power dividend. After that, the power dividend is constant. EA is constant. Yeah? Until I'm reaching where? The maximum speed. Omega max equal to what?
7.16.
Yes.
Omega.
10 to run the omega base. Why? Because the flux now is reduced by what? 0.1. So if I'm giving the rated, I'm reaching omega. If I'm going to 0.1 of the rated, I will reach 10 omega.
Yes.
10 omega of the base. Yeah? So this will equal to what? 7.16. Yeah? So now what I need, this one will go to where? Yeah, thank you. What about the torque? 0.3. Yeah, 0.3. Yeah, the torque is going to where? To 0.3. 0.3 somewhere here. Huh? I did it. Yeah. Good. Yes? So now here, I forced to go to the flux weakening before the rated speed. Why? Because I'm allowing the current to be higher than the rated value. Good? Good. And I will stop here. And this is the VA control. And this is what we call what? The flux control. And thank you for listening.